Welcome to this explainer. Today we're putting on our virtual X-ray glasses to uncover the unseen forces, futuristic engineering, and continuous mechanics that keep massive bridges from sinking. Have you ever really looked at a bridge and just wondered, how on earth does that thing stay up? Well, that's exactly what we're going to dive into today, the absolutely fascinating science of substructure stability.
To truly understand how millions of pounds of concrete and steel stay safely suspended in midair, we've got to look right past the roadway you drive on. We need to visualize the constant, hidden war against gravity. Because think about it. Gravity is the single most profound threat to any bridge, right? It's constantly trying to drag all that unyielding mass straight down to Earth. Since there's literally no support in the empty space below it, how do these massive structures actually survive?
Here is our blueprint of stability for today. We're going to cover 4 key areas. Number 1, the forces of compression and tension. Number 2, deep foundations and caissons. 3, the physics of floating bridges. And finally, number 4, the ultimate balancing act.
All right, let's jump straight into Section 1, Forces, Compression, and Tension.
Starting way high up in the air, the most critical challenge for any bridge is managing the dynamic loads of traffic plus the dead weight of the structure itself against that relentless pull of the Earth we just talked about. And every bridge survives by pulling off this perfect balancing act between 2 primary internal forces. First up is compression. You can think of compression as pushing and squeezing material inward, kind of like squeezing a tightly coiled spring. Then there's tension, which is the exact opposite. It stretches and pulls material outward, just like pulling a heavy rubber band. Bridge design is basically the absolute genius of balancing these compressive forces in certain spots with tensile ones in others.
You can really see how tension works on a massive scale with the Golden Gate Bridge. Those main cables are stretched in extreme tension all the way across the span. In physics, when you have a horizontal deck suspended on vertical rods attached to a main cable, the different forces acting on that cable cause it to take the shape of a parabola. It's this incredibly beautiful mathematical curve that's born entirely out of pure necessity and tension.
And notice how the deck's immense weight is actually managed. The vertical suspender rods are pulling the deck's weight up to those main cables. Then, the main cables, which are under that massive tension, transfer all those forces directly to the tall towers. And here's the trick. Those towers channel the weight as extreme compression straight down into the Earth. It's an unbelievably efficient system. You're basically moving forces from thin air directly down into solid ground. But, as you might guess, channeling thousands of tons of downward force into a riverbed introduces a really severe hidden threat just below the waterline.
Which brings us to Section 2, Deep Foundations and Caissons.
That hidden threat, it's called bridge scour. This is the dangerous erosion of sediment around the bridge piers caused by fast-moving water. The river essentially carves out these massive scour holes right at the base of the foundation. And get this, according to our sources, an estimated 60% of all bridge failures in the US are the result of scour and other hydraulic-related causes. 60%. That is wild. It absolutely forces engineers to build deeper, much smarter foundations that can actually withstand losing those top layers of soil.
So, to bypass all that unstable surface mud, engineers have to use deep foundations. They generally rely on one of 2 methods, either tightly grouped friction piles, which actually bond with the soil utilizing skin friction and overlapping compressive stress bulbs to support the weight, or they use caissons. These are massive, completely watertight concrete boxes that dig all the way down until they hit solid bedrock.
The really crucial point here is how they actually build these caissons in deep, muddy water. They sink what's called a pneumatic caisson. Basically, they float the open-bottom box, add concrete ballast, and then pump in compressed air to keep the hydrostatic pressure of the river at bay. This actually creates a totally dry chamber right at the bottom of the river. Historically, these incredibly brave workers called sandhogs had to dig in these pressurized environments, risking serious decompression sickness. But today, we use remote-controlled robotic crawlers equipped with high-frequency acoustic vision to safely excavate that muddy floor from inside the dry chamber. So as the dirt is removed, this heavy concrete box just sinks deeper and deeper until it finally hits solid rock.
But what happens in a place like Lake Washington in Seattle? The water there is over 60 meters deep, and it sits on top of another 45 meters of soft clay. If you wanted to build a traditional suspension bridge there, you'd need towers over 183 meters tall just to reach the bottom. Traditional towers and caissons are just completely impossible in those kinds of conditions.
So what do they do? Let's get into Section 3, the physics of floating bridges.
When the solid Earth is just way too deep to reach, structural engineers have to completely shift their mindset. They have to abandon the Earth and rely entirely on fluid dynamics. The ingenious solution here is a floating bridge. Now, these bridges might seem to defy gravity, but they don't float by magic, right? They rely 100% on Archimedes' principle. This is where the upward buoyant force of the displaced fluid perfectly counteracts the crushing downward weight of the bridge's dead load plus the live load of all those passing vehicles.
The engineering behind these pontoons is just incredible. For example, the State Route 520 floating bridge in Washington uses 77 massive concrete pontoons designed as hollow box structures. By filling these giant concrete structures with air, engineers maximize the displaced water volume. They trap enough air to keep the overall density of the pontoons far below that of the lake water. You're basically looking at giant concrete boats holding up a massive highway.
But just floating vertically simply isn't enough. A bridge has to resist wind, waves, and all that eccentric traffic load without, flipping over. So these wide, flat-bottom pontoons are designed to maintain a high metacentric height. That just means the metacenter is located well above the center of gravity. What this does is create a rotational righting moment. Basically, if the bridge tilts even slightly under heavy wind, the lateral displacement of the center of buoyancy generates a torque. That torque rotates the pontoon safely back to its upright, stable equilibrium.
Of course, you also can't just have a highway drifting away down the river. To keep the world's longest floating bridge perfectly aligned in the water, it's moored by 58 massive, high-strength steel cables. Each of these cables is nearly as thick as your arm, about 76 millimeters in diameter, and they are tensioned to an absolutely unbelievable 60 tons of force. To build a perfectly locked grid, those highly tensioned cables are pinned to the lakebed using a really specialized combination of advanced mooring anchors. First, you have fluke anchors that use their unique shape to dig deep into the soft silt. Then, gravity anchors, which are just massive concrete blocks that resist sliding purely through their immense mass. And finally, shaft anchors that are drilled directly into the solid bedrock near the shores. Working together, they absorb every single ounce of hydrodynamic stress the lake can possibly throw at them.
Which leads us to our final part, Section 4, the Ultimate Balancing Act.
When you think about the glowing tension vectors hidden inside suspension cables, or the robotic caissons digging deep into the riverbed, you realize a bridge is never truly at rest. It's exactly as this quote says, a bridge is a system of balanced forces where the superstructure interacts with the substructure to counteract gravity and environmental forces. They don't sink because they are carefully orchestrated machines of continuous mechanics. They're perpetually active, constantly taking the energy from heavy vehicles, pushing it through flexible cables and rigid columns, and gracefully channeling it safely back into the solid earth, or dispersing it right into the water.
So the next time you drive across a massive span, try to visualize those hidden forces stretching and squeezing right beneath your tires. Realize that you're being suspended by this delicate mathematical balance of compression, tension, and buoyancy. And honestly, it really makes you wonder, if this much unseen science and invisible force goes into simply getting you safely across a river, what other impossible engineering marvels are secretly holding up the rest of your world?